For decades, Voyager 1 has continued a journey that few believed would last this long. Launched in the late 20th century and originally designed for a much shorter mission, the spacecraft has now traveled approximately 18.5 billion kilometers from Earth, becoming the first human-made object to venture into interstellar space. Thanks to the careful use of its plutonium-powered energy system, NASA has managed to keep the probe operating far beyond its original expectations, turning it into one of the greatest engineering achievements in human history. Yet what makes Voyager's mission even more remarkable today is not simply its longevity. The information returning from the distant spacecraft is raising new questions among researchers. Although its remaining instruments continue to function reliably, some of the measurements being recorded in interstellar space do not fully match long-standing scientific predictions. Instead of confirming every expectation, Voyager is revealing a more complex environment than previously imagined, transforming a historic planetary exploration mission into an unprecedented investigation of the space between the stars. Before we continue, make sure to like this video and subscribe to the channel. Despite operating with only a fraction of its original power, Voyager 1 remains connected to Earth. To preserve energy, NASA has gradually shut down non-essential systems, including cameras and several secondary instruments, allowing the spacecraft to continue transmitting valuable scientific data. Even from the immense distances of interstellar space, Voyager still sends information back home, proving the effectiveness of the power management strategies developed over decades. While its signals now require more than 22 hours to reach Earth, the probe continues to provide scientists with insights that no other mission can offer. Year after year, the transmissions never stopped, faint and heavily delayed, yet remarkably dependable. Each signal carried observations from regions farther away than any place humanity had ever measured directly. Voyager 1 was doing far more than simply moving away from the Sun. It was venturing into territory completely unexplored by any previous spacecraft. That achievement alone secured its place among the most significant missions ever undertaken. As the distance increased, however, the mission evolved into something much larger. The focus was no longer limited to studying planets or moons. Voyager was approaching one of the most important frontiers in space science. For decades, astronomers described the outer boundary of the solar system through the extent of the Sun's influence. A continuous flow of charged particles known as the solar wind expands outward from the Sun, creating an enormous protective bubble called the heliosphere. Inside this region, the Sun's magnetic field remains the dominant force shaping the local environment. Beyond that boundary lies the interstellar medium, a vast region filled with gas, dust, magnetic fields, and energetic particles that exist between the stars. Separating these two domains is a transitional boundary known as the heliopause, and Voyager 1 was traveling directly toward it. Scientists believed they had a clear understanding of what would happen during this crossing. According to established models, the solar wind would gradually diminish, interstellar particle densities would rise, and the magnetic field should undergo a noticeable shift in orientation. Instead of following the Sun's magnetic influence, the field was expected to align with the broader structure of the Milky Way. Everything suggested that the transition would be unmistakable. The spacecraft would cross a clearly identifiable boundary, providing direct evidence that it had finally entered interstellar space. A clean separation, a measurable passage from one region of space to another. Voyager. It carried the necessary instruments to detect this transition. Even in its reduced state, it could still measure magnetic fields, plasma waves, and charged particles. In practice, it was a sensor steadily moving toward a line that scientists believed they understood. And as it got closer, the data began to change. The solar particles decreased, cosmic radiation increased, plasma density changed in ways that matched the predictions. Everything pointed to a single conclusion. A Voyager 1 was nearing its limit. But there was a problem. The closer it got to that boundary, the more crucial a single measurement became: the direction of the magnetic field. Because that was the signal that could confirm, without ambiguity, that the spacecraft had left the sun's influence behind. It was the detail that would separate theory from observation, expectation from reality. And when Voyager 1 finally reached this point, this signal did not change in the expected way. The frontier that hasn't changed. In August 2012, Voyager 1 reached the moment scientists had been waiting for. The instant it crossed the heliopause, the outer limit of the sun's influence. Based on decades of models, this transition should have been one of the clearest events ever recorded in space exploration. The predictions were specific. As Voyager approached the boundary, the solar wind would decrease dramatically. At the same time, cosmic rays coming from outside the solar system would increase. And most importantly, the magnetic field should change direction, ceasing to be aligned with the sun and becoming controlled by the galaxy. 3 signs: clear, measurable, and consistent. When the data started coming in, 2 of these signals appeared exactly as expected. The solar wind weakened, cosmic radiation increased. Everything indicated that Voyager had reached the edge of the heliosphere. But the 3rd signal, the most important one, didn't change. The magnetic field remained practically in the same direction. This shouldn't have happened. Entering interstellar space should be like entering a completely different environment. The magnetic field on the other side should have a different orientation, shaped by forces beyond the solar system. Instead, it was as if Voyager had crossed the boundary and found the same structure continuing on, like walking through a door and seeing the same environment. Initially, scientists hesitated. The data was clear, but the interpretation wasn't. Had Voyager truly crossed the heliopause? Or was it still within a region influenced by the sun in ways that were not fully understood? The measurements offered no simple answer. They created a contradiction, because if Voyager were still inside the heliosphere, the increase in cosmic radiation wouldn't make sense. But if it had left, the unchanged magnetic field wouldn't make sense either. The boundary was supposed to resolve this uncertainty. Instead, it created it. Subsequent analyses confirmed that the plasma density had increased significantly, exactly as scientists expected from interstellar space. This reinforced the idea that Voyager had indeed entered a new region, but the magnetic field continued to behave as if it were still connected to the sun. This left only one possibility. The boundary was not as scientists had imagined. Instead of being a clear line separating 2 distinct regions, the heliopause appeared to be more complex, a transition zone where properties of both environments overlapped. The sun's magnetic influence didn't simply stop. It extended outward, interacting with the interstellar medium in ways that blurred the distinction between inside and outside. This changed the meaning of the journey. Voyager didn't move from one clearly defined region to another. It entered a space where the rules were less clear, a space where the influence of the sun and that of the galaxy existed simultaneously. And this raised a deeper question. Because if the boundary itself wasn't well defined, then each measurement taken within it became more difficult to interpret. The data no longer described 2 separate systems. They were describing an interaction between them. And interactions are harder to model, harder to predict, and harder to fully understand. Which meant that the anomaly wasn't just the magnetic field. That was the assumption behind it, because everything about that crossing had been based on the idea that the edge of the solar system could be clearly defined. But the Voyager data suggested otherwise. They suggested that the edge wasn't a line, it was a region. And the moment scientists accepted that, a new question replaced the old one. The question was no longer whether Voyager 1 had crossed the boundary. The real mystery was understanding the nature of the boundary it had entered. Something in the data was not behaving as expected. After its historic crossing in 2012, Voyager 1 continued its journey without interruption. The spacecraft pressed onward, traveling ever deeper into what scientists classified as interstellar space. Researchers anticipated that once beyond the heliopause, the surrounding environment would gradually become more predictable and consistent. Far from the influence of the Sun, conditions were expected to reflect the larger structure of the galaxy itself. That, however, is not what happened. Instead of settling into a stable pattern, the measurements continued to reveal unexpected variations. The deeper Voyager traveled, the more scientists realized that the region beyond the heliosphere was proving to be far more complex than theoretical models had suggested. One of the most valuable instruments still operating aboard Voyager 1 was its plasma wave detector. This system measures oscillations within electrically charged particles, providing crucial information about the density and characteristics of the medium surrounding the spacecraft. By studying these plasma waves, researchers can effectively map the invisible environment through which Voyager is moving. According to existing theories, interstellar space should produce relatively steady readings, interrupted only occasionally by disturbances generated by major cosmic events, such as the shock waves created by distant supernovas. At first, the observations appeared to support those expectations. Voyager detected a series of plasma wave bursts that enabled scientists to calculate the density of the surrounding interstellar medium with remarkable accuracy. The results showed that the spacecraft was traveling through a region significantly denser than the outer layers of the heliosphere, providing strong evidence that it had successfully entered interstellar space. For a time, everything seemed to confirm the models, but as additional data continued to arrive from the darkness beyond the solar system, researchers began noticing patterns that were much harder to explain. But over time, the pattern of these signals began to change in ways that didn't fully match the models. Some of the variations were linked to known events, such as shock waves propagating through space from distant stellar explosions, but others emerged without a clear source. The density increased, then stabilized, and then changed again. These changes weren't extreme, but they were consistent enough to raise questions, because interstellar space, at least in theory, shouldn't behave like a highly dynamic system on this scale. It is vast, diffuse, and relatively uniform when compared to planetary environments. Small variations are expected, but not persistent fluctuations without clear causes. Voyager was detecting structure. At the same time, its cosmic ray instruments were recording changes in the intensity of high-energy particles. These particles, originating outside the solar system, should have followed predictable patterns once the protective effect of the heliosphere was removed. But even these readings showed variations that did not align perfectly with what was expected. What made this even more significant was the way these different systems began to overlap. Changes in plasma density, fluctuations in cosmic rays, and the behavior of the magnetic field were all showing small inconsistencies at the same time. The environment Voyager had entered was not as simple as the models suggested. It had structure, and that brought the focus back to the frontier. If the heliopause wasn't a clean separation, and if the region beyond it wasn't entirely uniform, then Voyager wasn't moving from one stable system to another. It was traversing layers, which meant that the fluctuations in its data weren't necessarily errors or anomalies. These could be measurements of something more complex than expected, something that hadn't been fully considered in the original models. And this changed the interpretation again, because now the question wasn't just about the boundary itself, but about the nature of space beyond it. The deeper scientists looked into the data, the more they realized that something important had been overlooked. By then, the pattern had become impossible to dismiss. Voyager 1 had clearly crossed the heliopause, yet the transition did not resemble the neat boundary researchers had anticipated. The region beyond it was far more complicated than expected. plasma densities continued to fluctuate. Magnetic fields failed to align exactly as theoretical models predicted. Even more puzzling, particles displayed characteristics of both environments, creating an overlap between regions that were supposed to be distinctly separate. At first, researchers treated these findings as isolated irregularities, but as the evidence accumulated year after year, a new possibility began to take shape. Perhaps the problem was not with Voyager's measurements at all. Perhaps the assumptions behind the models needed to be reconsidered. For decades, scientists described the heliosphere as a vast protective bubble surrounding the solar system. Created by the outward pressure of the solar wind, it was thought to form a relatively clear boundary where it met the interstellar medium. The heliopause was considered the dividing line where these opposing forces reached equilibrium. Reality, however, is often far more complex than theory. As researchers reanalyzed Voyager's observations, they began to suspect that the heliosphere might not be a smooth or symmetrical structure. Instead, it could be an irregular and constantly evolving region, shaped by powerful external influences that had previously been underestimated. Among the most significant of these influences is the interstellar magnetic field. Unlike the Sun's magnetic field, which extends outward from our star, the interstellar field operates on a much larger galactic scale and is affected by the motion and structure of the Milky Way itself. As the solar system travels through this environment, the two magnetic systems inevitably interact. This interaction produces a phenomenon known as magnetic draping. Rather than passing straight through the heliosphere, interstellar magnetic field lines bend and wrap around its outer surface. The result is not a sharp dividing line, but a complex transitional region where solar and interstellar magnetic fields overlap, interact, and influence one another. This realization changed the entire interpretation of Voyager's observations. If the interstellar magnetic field is being bent around the heliosphere, then a spacecraft crossing the heliopause would not necessarily detect an immediate shift in magnetic direction. Instead, it would encounter a degree of continuity between the two regions. Remarkably, that is exactly what Voyager recorded. The magnetic field did not undergo the dramatic change scientists had expected because the boundary itself was not behaving like a simple border. It was being shaped by the simultaneous interaction of two enormous magnetic systems. Yet even this explanation left important questions unanswered. Magnetic draping could account for the continuity of the field, but it did not fully explain the layered fluctuations and variations that Voyager continued to observe. To solve that mystery, scientists turned their attention to another possibility: turbulence along the boundary itself. Rather than remaining fixed and stable, the heliopause may be a dynamic and constantly shifting region. In this scenario, particles from the solar wind and the interstellar medium can intermingle, exchange energy, and create pockets of instability. The boundary behaves less like a solid wall and more like a flowing current, where different regions interact and evolve over time. Such an environment would naturally generate the irregular patterns, density changes, and magnetic variations that Voyager has been detecting for years. What once appeared to be anomalies may actually be evidence that the edge of our solar system is far more active, complex, and unpredictable than anyone previously imagined. Plasma densities would fluctuate, particle distributions would change, and magnetic fields would appear consistent in some areas and slightly altered in others. The signals sent by Voyager take more than 20 hours to reach Earth. What scientists analyze is not real-time data. It is a belated snapshot of conditions that may have already changed by the time they are observed. This makes it even more difficult to reconstruct a stable picture of the environment. All of this points to a single conclusion. The region around the heliopause is not a boundary in the traditional sense. It is a zone of interaction, a place where forces overlap, compete, and continually reshape each other. And Voyager not only crossed it, it is still moving through it. This means that the fluctuations in your data are not merely traces of a transition. They may be ongoing measurements of a system that we don't yet fully understand. And this leads to a deeper implication. Because if the outer edge of our solar system is so complex, then the idea of a clear separation between inside and outside may simply not apply. And that changes how we think about where the solar system actually ends, where the solar system truly ends. At the moment when Voyager, when a point was crossed, which scientists called the heliopause, this should mark a clear milestone. But the data never fully supported this idea. Because if the heliopause is not a defined boundary, if it is a region where solar and interstellar forces overlap, then the concept of an edge becomes more difficult to define. Voyager didn't just pass from one side to the other. It entered a zone where both environments still exist simultaneously. Inside the heliosphere, the Sun dominates. Outside of it, the galaxy dominates. Voyager data suggests that this distinction may not be absolute. Instead, the solar system may extend farther than we imagined. Not as a defined structure, but as an influence that gradually diminishes. The Sun's magnetic field, its particles, and its energy do not simply stop at a straight line. They weaken, interact, and blend into their surroundings. This means there may not be a single point where the solar system ends, but rather a region where it gradually disappears. And this has real consequences for how we interpret Voyager's position, because although it is technically in interstellar space, it still detects effects linked to the Sun. The alignment of the magnetic field, the behavior of the particles, and the plasma fluctuations suggest that the influence of the solar system has not yet completely disappeared. This also explains why Voyager's data doesn't fully match interstellar models. These models assume a cleaner environment, where local influences are minimal. But Voyager is measuring a space where these influences are still interacting, a space that is not completely one thing or the other. This means that each reading sent by Voyager is part of a larger transition, not a fixed state. Transitions are more difficult to interpret than stable systems. They contain overlapping signals, variable conditions, and interactions that do not stabilize into predictable patterns. That's exactly what Voyager has detected. And that leads to a more accurate way of understanding what Voyager actually did. She didn't reach the edge of the solar system. She reached the limit of how clearly we can define that edge. Because if the border itself isn't fixed, then the idea of crossing it becomes less significant. Voyager didn't leave one known region for another. It entered something that is still being defined. If the solar system doesn't end where we thought, then what exactly have we been measuring all this time? What is Voyager really showing us? After everything that Voyager 1 observation noted, that the biggest change is not in the data itself, but in how that data is interpreted. For many years, scientists viewed the space beyond the solar system as a relatively straightforward environment. It was believed to be an immense and largely empty expanse where particles drifted through the darkness, magnetic fields stretched across enormous distances, and physical changes occurred gradually over long periods of time. Crossing the heliopause was expected to mark the beginning of this simpler and more predictable realm. However, the data returned by Voyager 1 has painted a very different picture. Rather than revealing a clean and clearly defined border, the spacecraft has uncovered evidence of a remarkably complex transition zone. The observations suggest that the boundary between the solar system and interstellar space is not a rigid dividing line, but an active region where magnetic fields, charged particles, and energetic forces constantly interact with one another. Instead of remaining separate, these environments overlap, creating layers of influence that shift and evolve over time. What Voyager discovered was not a contradiction of established physics. The laws governing the universe remain intact. Instead, The findings exposed the limitations of the simplified models scientists had relied upon for decades. Those models often treated cosmic regions as distinct domains with well-defined boundaries, when reality appears to be far more interconnected. In many ways, Voyager's greatest contribution has not been the discovery of a single unexpected phenomenon, but the realization that our understanding of the universe's outer frontiers is still incomplete. The probe has shown that the edge of the solar system is not a simple threshold, but a dynamic environment shaped by the continuous interaction of forces operating on both stellar and galactic scales. More than 40 years after its launch, Voyager 1 continues to remind humanity of a humbling truth. The farther we explore, the more we discover that the universe is richer, more intricate, and more mysterious than our theories once imagined. What lies beyond our solar system is not merely empty space. It is a frontier that is still teaching us how the cosmos truly works.